Good evening, class. We just had a chat about what's happening for the exam. And now we're going to start the lecture. We were looking at section 5.3. And it's exponential function. So we're going to recap quickly what we've done. And that is the definition of an exponential function, f of x is a to the power of x. The restrictions are as follows. A must be positive, A can't be 1. We've discussed the reason. When A is 1, you get a horizontal line. And if A is positive, it results in a 1-to-1 function, which has an inverse. The general shape of exponential function, when the base is positive, it's an exponential growth. And when it's negative, it's an exponential decay. So we looked at 2 to the power of x and 3 to the power of x, and for all practical purposes, they look the same. If you put them on the same set of axes, f of x gets closer and closer to the y-axis on the right side, and you see that. So that's important to understand. So if I go back to this page, if you compare the top left picture, 3 to the power of x versus 6 to the power of x, you notice that 6 to the power of x is closer. This is the blue one, and it's closer to the y-axis. Both of them go through the same y-intercept, namely 0, 1. Now, so what's in common? Very simple. The intercept, x-intercept doesn't exist. Y-intercept is 0, 1. Domain is all real numbers. Range goes from 0 to infinity, the positive side of y. Horizontal asymptote is the x-axis, has the equation y equals 0, and there is no vertical asymptote. Now, if you remember the graph, you remember everything that is given here. And needless to say, it's an increasing function everywhere. We look at 1/2 to the power of x. When we graph it, it becomes an exponential decay, and every property is the same as the previous page, with the exception that in the previous page, the function was an increasing function, but now we are dealing with a decreasing function. So we did that by plotting points. We also looked at it from the point of view of transformation. Exponential function 2 to the power of minus x minus 3. We mentioned 2 to the power of negative x. You have a choice. You can start with 2 to the power of x, flip it over with respect to the y-axis, and then shift it down by 3 units. Or you can start with 1/2 to the power of x, because 2 to the power of negative x is the same as 1/2 to the power of x. So let me quickly put that up for you. Okay. So as we saw, this is the same as what? 1/2 to the power of x minus 3. And 1/2 to the power of x, you should be able to see this is the graph of interest. Okay. So that's the graph, and we discussed what happens when it comes to the intercepts. And I hope everybody remembers that. Just a quick recap is that you set this one equal to 0, and sorry. and you solve it. Okay, which means you move the -3 and you take the natural log. So a quick recap on that. 2 to the power of minus x is 3. If you take the natural log of both sides, then you end up with -x ln 2 equals ln 3, and x becomes negative ln 3 over ln 2, and that is located there.
Professor,
Okay, class?
is it ln or log? Because I thought last time it was log.
It's ln. We take a natural log. You can take a log, or it makes no difference. So let me write this. X is minus ln 3 over ln 2, which is equal to minus log 3. The change of base formula says you can rewrite it with log of the 3 over log of the 2. Don't forget there is a negative sign, and you can use any base. You can use the base e, natural log. You can use base 10, common log, or you can use any other base. That's the change of base formula. So whether you use ln 3 over ln 2 with a negative sign, of course, because everybody can see why we have a negative sign, or log 3 over log 2 makes no difference. Sounds good, everybody?
Yes.
Yeah.
Perfect. And so here's the next one. First and foremost, the definition for the E, as you look at the last column, because this is posted, I just want to make a point. First of all, the graph looks like 2 to the power of x or 3 to the power of x and so forth. Of course, if you were to have 2 to the power of x as well as 3 to the power of x, then this would be between the two, okay? So I hope you can imagine, and the reason why is because E is 2.71828 and it continues indefinitely. So if you look at the last column, okay, and you see that this seems to be the value of the E, and this is by the following limit. If you take the limit as n goes to infinity of 1 plus 1 over n to the power of n, and we prove that in calculus. So again, bear in mind that E is between number 2 and 3. It's closer to 3 than 2. So the graph is also between 2 to the power of x and 3 to the power of x, okay? So I can try to give it a shot. So this is by no means to scale. So this would be like y equals 3 to the power of x. This would be like y equals 2 to the power of x. And e to the power of x is in between. The graph doesn't look good. I have a hard time writing and drawing class, as you know. So it's easy to recognize which one is which in case. All right. Those are the definitions, class. as far as the E is concerned. 1 plus the limit as n approaches infinity of 1 plus 1 over n to the power of n. If you replace the 1 over n, if you let 1 over n be, let's say, x or h, then you replace it with that, and when n goes to infinity, when n becomes huge, h becomes 1 over a huge number, which is 0. That's why when you look at the limit, the concept of a limit, in this case, n is approaching infinity, it's the same as h approaching 0. So that's, I hope it's very straightforward. And again, we discussed this in calculus. And the second one, also, we use calculus to prove it when we differentiate exponential functions. The first one, however, the proof, we have seen a basic proof in algebra, college algebra, but a more proper one is in calculus, in any event. All right, we want to graph this using a transformation. There are a couple of simple transformations, and I'm going to assume everybody knows y equals e to the power of x looks something like that. So there are two transformations. I'm going to pause the recording, give everybody a chance to come up with the answer, and then we move on. So let's pause the recording. All right. There are basically two transformations. One of them happens here. X is replaced by x minus 3, and one of them happens here. So that x minus 3 will shift it to the right by 3 units. That negative in front of a function will flip it over, and it really doesn't matter in what order you do it. Either way will do the job, because this is simple enough. Generally speaking, as you know, I'm interested in the order of operations to make sure it works out nice and easy. So if you flip it over with respect to the x-axis or reflection, you end up with this transformation. Replace the x with x minus 3. That means move it to the right, and you end up with this transformation, which is the answer. Now, as far as the properties, I hope you see the graph and you see the properties. For example, the domain hasn't changed, still all real numbers, but the range, which was originally 0 to infinity, now it's actually from negative infinity to 0, and the function which was initially being e to the power of x, an increasing function, now is decreasing. Okay, and so the asymptote doesn't change. So this is the information. So x-interceptor is none. Y-intercept is at 0, negative e to the power of negative 3. Can anybody tell us how we get to the y-intercept? How do we find the y-intercept? Class, anybody want to share with us the answer? All right, to find the y-intercept, as always, you set x equal to 0. When you set that x equal to 0, then it becomes minus e to the power of 0 minus 3, which is minus 3. And this is the precise answer. And if you look at the graph, it's there. And that's your y-intercept. I hope everybody is comfortable finding intercepts. All right. We're going to move on. Any questions? Okay.
I got it.
Perfect. All right. We want to solve these two equations. They are fairly simple. We're going to look at and start with the first one, part A, 2 to the power of 3x minus 1 equals 32. If you look at the bottom, the property says if you have exponential functions that are equal and they have the same base, they must have the same exponent. So when we look at part A, all we have to do represent 32 if it's possible, not always, with a base 2. And 32 equals 2 to the power of, anybody? Thirty-two equals 2 to the power of 5. So practically you're done. Now 3x minus 1 equals 5, and that's an easy solve. We're not going to, you know, bother putting too much effort solving that. As long as we rewrite 32 as 2 to the power of 5, we are done.
So you just changed the base of 32, and you want to match to the base of the opposite side of the equation to 2.
Yes.
So it'd be an exponent. Then you set the exponents to an equation and solve for x, right?
Perfect. And the thing is, if it's not doable, if there is no way to come up with the same base, in other words, the left side and the right side, if they have the same base, it makes life easy. If not, then you have to take a log of both sides. That means natural log, common log, you name it. If I couldn't come up with the same base, I would say ln of the left side is equal to ln of 32. And then 3x minus 1 becomes the coefficient, and I go through the process of solving it, which is more complicated. But, I mean, it uses logarithmic properties. And I hope everybody has studied them and they are fairly comfortable with that. Now, when we look at part B, the left side has the base e. All we have to do on the right side, just simplify it. Okay, so as you can see, 1 over e to the power of 3x, okay, times e to the power of minus x times 4. That means you can bring e to the power of 3x up, becomes e to the power of minus 3x. And the other one is e to the power of minus 4x. Or you can write down e to the power of minus 4x divided by e to the power of 3x. Either way becomes e to the power of minus 7x. Everybody can see how we arrive at e to the power of minus 7x. Right, class?
Yes.
And you're practically done because now we set 2x minus 1 equals minus 7x. And that's an easy question to solve. If you move the negative 7x, the left side becomes 2 and 7, 9x. Negative 1 goes to the right, becomes positive 1. X is 1 over 9. All right. We're going to look at a few more examples like this just to make sure everybody's comfortable with this. Okay, a couple more examples to be on the safe side. Same thing, we can easily come up with the same base. So let's discuss part A, and then I give you a chance to work on part B. Part A, the left side is 3 to the power of x plus 1, and you're done. What about AD1? We can write AD1 as 3 to the power of what, class? Anyone?
4.
4, perfect. And you're done. X plus 1 is 4, and x is 3. It's a very simple case. Now you want to do the same thing to part B. So let's give everybody a chance to figure it out. 1 minute. And so I'm going to pause the recording. All right. First of all, the exponent on the right side is x plus 3, as it was mentioned while we were pausing the recording. Left side has the base 4, right side has the base 8. We have to make sure they are having the same base. So 4 becomes 2 squared, 8 becomes 2 cubed. Now, by the power rule, you have to multiply the exponents. 2 times 2x minus 1 for the left, and 3 times x plus 3 for the right. And they are equal. And this is an easy solve. X becomes 11 when we go through the process, because the left side is 4x minus 2. The right side is 3x. So when you combine these two, you get x. When you combine those two, you get 11. In other words, negative 2 goes to the right, becomes positive 2. 3x goes to the left, and it becomes negative 3x. X is 11, and you can check. You can put it back in and check. All right. Here's the next one. We want to come up with the same base on both sides. Let's discuss part A because it shouldn't be a big deal, fairly simple. So we can quickly see that the base is E on both sides. So the left side, there is nothing we can do. It's e to the power of minus x squared. Can anybody tell me what happens to the right? In other words, the right side is e to the power of what? Anyone?
One over x squared.
All right. Why don't we discuss the first piece? E to the power of x to the power of 2. How do we rewrite that? What is e to the power of x?
E to the power of 2x.
Okay, 2x. That's it. What did I do? Okay. Sorry, let me just see something went wrong. All right, yes, this is e to the power of 2x. Okay, because x times 2, that's the power rule. And then you're dividing by e cubed, 2x minus 3. I hope you see that. This is a very simple case. And now the exponents are equal. You have to solve a quadratic equation by putting negative x squared on the right side. When you factor this, I have a feeling nobody has any problem factoring this. We end up with the factored format x plus 3 times x minus 1. And that means x is either negative 3 or positive 1. Sounds good? Everybody?
Yeah.
Perfect. Why don't we think about part B? It's really not too bad, okay, class? All you have to do, figure out what base you want to use, and it makes it obvious the right side, the base must be 3. So if you can come up with the proper method for the left, you should be done in no time. So what should we do on the left side? What
Change the
can we
basis to
do?
3.
Yeah, so how do we then change that?
9 would be 3 squared,
Beautiful.
and 27 would be 3 cubed.
Perfect, perfect. So practically we are done when we see that. So 9 changes to 3 squared, then 2 times 2x is 4x. 27 changes to 3 cubed, and so 3 to the power of 3x squared. And the left side becomes 3 to the power of 4x plus 3x squared. The right side is not changing, so the exponents are equal. And that means 4x plus 3x squared equals -1. Now you bring it to the same side and you do proper factoring and you're done. So when you put it on the same side, you put it in descending order, 3x squared plus 4x plus 1. It's a very simple factoring because 3 is a prime number and therefore it's 1 times 3, so x and 3x, and at the end plus 1 is just 1 times 1 or -1 times -1, and we end up with this. So the answers are -1 or -1/3. All right, sounds good, everybody?
Yeah.
Yeah.
Perfect. Here's the next example, the last one we're going to look at. F of x is c b to the power of x, where c is some sort of a number, a constant. B is some sort of a number, but when we use different variables, that means 2 different numbers, okay? So how do we come up with the exponential function? We need to find C and B using the fact that the 2 pairs are given. So clearly from the graph, everybody can see the 2 pairs. So now, what do? We plug in the first pair and we write it. We plug in the second pair and we write it. So let's give everybody a moment to do that. Can you plug in, I don't want you to solve it. If we can plug in, I assume we can solve it. Can you plug in the first pair and see what you get? And plug in the second pair and see what you get. All right. When we plug in -1, 3, we get f of x is 3, so 3 equals c times b to the power of x or -1. Does that make sense, everybody?
Yeah.
We replace the y or f of x with number 3. We replace the x with -1. We do exactly the same thing for the second pair. 1, 4/3, we do exactly the same thing. And we are practically done. We have 2 equations and 2 unknowns. This is a system of equations, but it's not necessarily linear. So basically, you can find the relationship between C and B in one of them and put it into the next one. For example, if you look at the first one in green, 3 equals CB to the power of -1. That means C over B. And the cross product gives us C equals 3B. Now we put that into the second equation and we write 4/3, which is equal to CB, is the same as writing 3B times B. Okay? 4/3 equals CB, and we replace the C with 3B. Now we are practically done. Okay? The left side is 4/3. The right side is 3B squared. You can divide both sides by 3 and you get B squared equals 4/9. And B is plus minus 2/3.
And then you plug in B to find A. I mean C, sorry.
Exactly.
Okay.
And so plus minus 2/3. This shouldn't be there. Plus minus 2/3. And we have 2 choices, but we choose the positive because, as you recall, we choose the base to be positive on purpose to make sure it's a one-to-one function, as you know. And now all you have to do, look at this case and say, we know C is 3 times B. So 3 times 2/3 makes it 2. And the function becomes 2 times 2/3 to the power of x. All right, any questions? Everybody's okay with this? We are ready to move on because I want to go to the next section, class.
I don't
No
understand.
questions.
Yeah.
Okay, go ahead. What's the question? Go ahead. Yes, go ahead.
Didn't you say it was 4/3 equals CB equals 3B squared?
Okay, that's right.
And then you erased it and then you wrote equals 3B at the end.
We are okay with this, right?
Yeah.
Yeah.
Yeah, that's fine.
If you divide both sides by 3, you get 4/9 equals B squared. Is that right?
Yes.
Okay. That makes much more sense. Thank you.
Yeah.
So the rest should be very straightforward. B is plus minus 2/3. And as I mentioned, this is wrong, okay? Plus minus 2/3. So there are two answers. We choose the positive answer because we are dealing with an exponential function and the base must be positive.
Positive.
And then you use the fact that c equals 3b, and so 3 times 2/3 gives you number 2. 3 times 2/3. And then you use f of x equals c b to the power of x and write the answer. Sounds good? Can I assume everybody is done so we can go to the next section,
Yes.
class?
Yeah.
Perfect. Again, I'm assuming no questions. If you have a question, please stop me. Let's see, everybody can see section 5.4, logarithmic functions?
Yeah.
Okay. All right. So that's fine. And just want to make sure that we can see that and nothing else. So one more time, we are looking at section 5.4, right, class?
Mhm.
Okay, perfect. Because I have a couple of sections up and open. I want to just share one at a time. All right, we got to resume the recording. No, I think the recording is on. Just all right, class. So with that being the case, we are looking at logarithmic functions. We looked at composite functions, one-to-one functions, inverse functions, exponential. And now we are going to look at logarithmic functions. And I hope everybody remembers some of this from before. So, first of all, the way we read it, we have to mention the base somehow, okay? So for example, you can write log x base a as the log of x to the base a, or log base a of x, or even log x base a. The base has to be mentioned, okay? So what I want you to pay attention to is this definition and how you go from one format to the next. In both cases, the base is the same, namely b. In both cases, y is considered to be the exponent, In the case of exponential format, x is the result. In the case of logarithmic format is the argument of log. So this is called the argument of log. Argument. All right. As long as we can go to from one format to the next, we are fine. So then we consider the right side. What is the meaning of this log if we start with an exponential function 2 to the power of x? Okay. You interchange and you get x equals 2 to the power of y. So f inverse of x is the exponent to which we must raise 2 to get x. And so we have the symbol as a result. Okay. So the symbol representing the inverse is this, the log. That's the bottom line. Okay. So what we really should recognize, this very simple transformation from one format to the next. If I see the exponential format, I can go to the logarithmic format and vice versa. So therefore, what is log? Log is simply an exponent. In other words, one might say, just putting this question into perspective, one might ask, okay, 2 to what power is 8? Or one might ask log, okay, 8 when the base is 2 is what? They are asking the same question in two different formats. And that's the idea that I'm hoping everybody gets out of this, and therefore logs become fairly nice and easy. And that is the following. Log is simply an exponent. So 2 to what power is 8? Everybody knows the answer. 2 cubed is 8, therefore the answer is number 3. So log 8 base 2, what is the answer? Same answer, number 3. All right, to make sure we can handle this, let's write in logarithmic form and in exponential form. Okay, so if you are given 7 to the power of x equals 15, you should be able to come up with logarithmic format. How would you come up with that? So can somebody quickly give us part A? I'm hoping this goes fast. Part A, how do we rewrite that in logarithmic form?
Is it
Log okay, take a look at this top. Take a look at this one, everybody. Take a look at this one. Make the transformation. We had this in intermediate algebra. Then we repeated it in college algebra. And now it's pre-calculus. So look at that. How do you write 7 to the power of x equals 15 in logarithmic format? Anyone?
log of 7? Oh,
Log 15 base
Seven.
is what?
Base is 7.
Equals x.
Yes, that base 7. Okay.
So log base 7 or log to the base 7 of 15 is x. I want you to write B and C for yourself quickly and then answer the question. Part B, we are going to rewrite it as what? Log,
Log base pi m equals
Perfect.
3.
Beautiful. X to the power of 5 is 12.
That one's log base x 12 equals 5.
Yeah, very simple. Thanks. That was great. So it's that simple, everybody. When it comes to the second part, and we want to write the exponential format, I want you to pay attention to this arrow class that I'm going to do. Everybody pay attention. If you follow this arrow, it means 3 to the power of what? Class?
4.
4.
That's it. You're done. You do the same thing here. And the answer
Power
is?
of 2 equals
Oh.
5.
No, it's x to the square. Yeah.
X squared is 5, yes?
Mm-hmm.
Yes.
Last one?
3 exponent x equals 8.
X equals 8.
That's simple. So everybody is okay and happy with it, I hope.
Yeah.
Perfect. We're going to move on. I expect you to be able to do this in a split second. You need to be very comfortable with this class. All right. Okay, so we wrote them in a proper format. The first batch in logarithmic form and the second batch in exponential form. Now, as far as graph is concerned, let's do this quickly. We've seen it in intermediate algebra and then in college algebra. Let's quickly do that with plotting points, because when we start a function and we don't know anything about it, that's how we do that. Then it becomes an easy function to remember. The choice that we put on the base is the same as what we did for the exponential, for the same reason, because we want it to be a one-to-one function. So a must be positive, a can't be 1. Same reasoning for the exponential function, okay? If a is 1, 1 to any power, okay, remains as 1, and a can't be negative. We want to keep it as positive to have a function which doesn't oscillate, and it's 1-to-1. So having said that, all we have to do, pick up a bunch of pairs, okay? And to do that, it's easier to go to exponential format. So the way it's given, again, we may not be that familiar with log. We are going to transform it into x equals 2 to the power of y. And now, I hope you realize the easy variable to pick would be the value of y and then calculate x. For example, if y is 0, then x is 2 to the power of 0, which is 1. If y is, let's say, 5, then it's 2 to the power of 5, which is 32 for x. If it's negative 1, the choice for y, then x is 2 to the power of negative 1, which means 1/2. So we start with the y coordinates first, and we get the x coordinates, and we graph this carefully. And it looks something like this. So what do we notice as the properties? I hope you see that if you recall, the domain for exponential function was all real numbers. Now the range is all real numbers. The range was 0 to infinity, and now the domain is 0 to infinity. The y-intercept was 0, 1 for the exponential function, and now it's the x-intercept. We had a horizontal asymptote, okay, which was the x-axis, and now we have a vertical asymptote, which is the y-axis. So I hope everybody can see that from the graph we can answer this. Needless to say, it's an increasing function. We can answer all of these questions from the graph. And this works for any log as long as the base is larger than 1. At the same time, the two functions are inverse functions, logs versus exponential. So we can see that everything that works there, we can see it in the form of an inverse function. All right, so what we want to do, we want to give the synopsis of what we have noticed so far, okay, as far as the graphs are concerned. So exponential functions and logarithmic functions are inverse of each other. So with that being the case, they look like this as if you put them on the same set of axes. Now, the way we have those graphs, A is larger than 1. I want you to know that. So the choice of A is larger than 1 results in what you see, and obviously inverse functions are symmetric with respect to the line y equals x. Properties of logarithmic functions, properties of exponential functions. And so we can compare and contrast. And because they are inverse, it's very easy to see x-intercept is 1, 0 for log, none for exponential, but the y-intercept for them becomes 0, 1, and the rest of them follow. So I hope everybody's okay with this page. What we are going to do, we're going to quickly look at the next example. I want to give everybody a chance to graph this fairly nice and easy. So we want to graph y equals log x base 3, and if you do just a basic graph for me, again, we are just looking at perhaps plotting some points, but ultimately for a case like that, I just want the general shape, and that's good enough. Well, first we rewrite the logarithmic format using exponential format. Then we choose the y because it's easier. For example, if y is 0, then x is 3 to the power of 0, which is 1. If y is 1, x is 3, so on and so forth. So these are a few pairs. If you plot them carefully, you notice that y equals log x base 3 is very similar to log x with base 2 or 5 or 7, as long as the base is larger than 1, it looks like that. Now, the larger the base, the smaller the y coordinate, which means if we have log x, let's say base 5, it gets closer to the x-axis now instead of the y-axis. Y equals log x base 2, then it gets further away from the x-axis. Okay, so that's important to pay attention to. So when the base gets larger, the y gets smaller, the graph gets closer to the x-axis. Also, I have the inverse function y equals 3 to the power of x, so you can see the graph and how it works. Okay. Remember, in the case of exponential function, the larger the base, the closer to the y-axis. In the case of a logarithmic function, the larger the base, closer to the x-axis. Sounds good, class? We're going to move on.
Yeah.
Okay.
All right. Let's say we want to evaluate those, and sometimes it's easy. We know the answer practically, and we're done. But the idea is that if you look at the first one, for example, let's start with the easy one. Log base 3 of 81. That means 3 to what power is 81? Okay, that's the meaning of it. All right. So we write down 3 to the power of. So what we can do, we can set this equal to anything we want, x, y, z, okay, and do the math. So if we set this, for example, to y, we have 3 to the power of y is 81. We already know from the previous section. All we have to do, rewrite 81 as 3 to the power of 4, and we are done. Okay. Same thing happens with part B. Let's say we don't know the answer. We say, okay, let it be something, any variable of your choice. X, Y, Z, A, B, C, D, your choice. And we rewrite it in an expression format, and it makes it 2 to the power of x is 1 over 8. Again, very simple. We want to write both sides the same base if possible. The left is 2 to the power of x. The right is 1 over 8. And we is 2 cubed. So we can rewrite this as 2 to the power of negative 3. Therefore, x becomes negative 3. Sounds good? Everybody okay with this? Any questions, class?
No, thank you.
My pleasure. All right. We want to find the domain of a log. If you recall, for the basic log, we said the argument must be positive, and the domain was from 0 to infinity. So all we have to do, set this one. Instead of x, now we have x minus 2, larger than 0. This is a simple case. X is larger than 2, which is the same as 2. Now, part B class works out the same. The argument of log is x plus 3 over x minus 1. So that one must be larger than 0. I'm not going to go over the way we come up with the answer, but can anybody tell us how we got the answer for a case like this previously when you have a nonlinear function larger than 0? What was the process? Even if it's in the form of a fraction, makes no difference, or in the form of a product, what do we do? Class? If you were to find the answer, what would you do? Can anyone share with us?
Would we go x minus 1 greater than 0 and solve for x?
No. No. It's the whole thing, x plus 3 over x minus 1, that must be larger than 0. What did we use?
Do you have to find the limits? No.
Limit? No. Nobody remembers that? Sine graph. Do you remember that, everybody?
Oh, is it though? Okay.
Do you remember that, class? We did sine graph, didn't we?
Yeah.
Yeah.
Exactly. Which means you put the top 0 and it gives you -3. You set the bottom equal to 0 and it gives you 1. So you have -3 and you have 1. You do the sine graph by picking up a test point and find out what happens in each region. I'm going to assume you can finish this on your own, and that would be the answer. From -∞ to -3, union to 1 to infinity. What I'd like you to do is to make sure you can do the sine graph on your own. And if you have a question, you can ask me next time, because we have gone through that extensively. Okay? Sounds good?
Yes.
Everyone?
Yep.
All right.
Yeah.
Now, same thing. We have to write the argument larger than 0. So x minus 1 must be larger than 0. And do you remember how we take care of that? How we take care of absolute value inequalities? Anybody remembers that?
Well, in this case, wouldn't it only just be the x minus 1? Because if we do the x minus 1, x plus 1, wouldn't only the x minus 1 be true?
No, I'm talking about solving inequalities involving absolute value.
You set both of them to 0 then.
Class, when absolute value of x equals k, the answer is x equals plus minus k. I'm refreshing your memory about equality if k is positive. We are assuming the right side is positive. If it's less than k, it's sandwiched between negative and positive. And if it's larger than k, we are assuming k is positive, okay? Then the result will be x less than minus k, or x is larger than k.
Well, yeah,
Okay.
Professor, that's what I meant when I said earlier. But in this case, wouldn't only the x minus 1 only work? Because it's saying,
Yeah, well, the right side is 0, so what happens, it ends up being x minus 1 less than 0 or x
Both work still.
minus 1 larger than 0. And that's a simple inequality. The first one says x is less than 1, so minus infinity to 1. The second one says x is larger than 1, that means 1 to infinity. And so what really matters to understand here, anything in between doesn't work. That means you can pick any number you want except 1. That's really the idea behind that. In other words, the only thing that makes this everything that you choose makes this non-negative, with the exception of 1. 1 makes it 0. If you recognize that, you don't have to go through the process I mentioned. All you have to do, write down, basically from here, you can say x is fine except 1, and then that in the interval form is what you can see. Does that make sense? Is everybody okay with that?
Yeah.
Yeah.
Perfect. We're going to move on, class, to the next example. So this example is a word problem. Of course, it's a very simple one. It just takes a long time to write. It's posted. Could somebody be kind enough to read this question for us fast, please?
From the beginning,
Yes, please.
the function p equals 95 minus 30 log base 2x models the percent p of students who recall the important features of a classroom lecture over time, where x is the number of days that have elapsed since the lecture was given. What percent of the students recall the important features of a lecture 8 days after it was given?
Thank you so much. And so basically what it means, use the formula given and replace the x the formula given, replace the x with 8 days. And so it's a simple case. You plug in, by the way, log 8 base 2, you may know it's 3 by now, and you end up with 5. So according to this study class, only 5% of the students remember the lecture. That's scary, isn't it, class?
Yep.
Sadly, this is true. As of course I was going through this lecture, I asked some questions and most students couldn't answer it, I believe. So that's the reason I picked this question for you, to wake you up. The only way you remember is by studying and restudying, and there is absolutely no way around it, class. Okay? All right. We're going to move on. The next topic deals with natural exponentials. We've already discussed the base is e. The reason we use a letter to represent that is just like pi, because it's a very important base. It's an irrational number just like pi. So there are the decimals, they are non-terminating and they keep on going, and they are non-repeating. That's the definition of actually an irrational number. So with that being the case, since e is larger than 1, so it follows, remember, for the exponential, y equals e to the power of x and how it looks. Now the same thing for the log. and we use ln to represent that, it looks like any log with the base larger than 1. Okay, so the base is e. When we say log x base e, it means ln x. So we are going to drop the base and we are going to replace the log with ln. I hope everybody remembers that from before. Okay. So that's in honor of John Napier. So here's the two functions. As you can see, y equals e to the power of x looks just like, very close, like y equals 2 to the power of x or 3 to the power of x. Y equals ln x is its inverse, and it looks like y equals log x base 2 or base 5 or base 3, and you name it. So what you really need to know, you should remember the general shape. Also, you may remember common log. Base is simply 10. When the base is 10, everybody, we just write log with no base. So just to quickly recap this. Natural log, the base is e, we use ln to represent. We don't write the base. Common log, we use log, no base. The base is 10 for common log. In both cases, we can rewrite the log into exponential format. Equals ln x is the same as x equals e to the power of y in its exponential form. Y equals log x is as equals 10 power of y. All right, I hope that is coming to us. All right, we want to graph this function. We want to this domain, range, asymptotes, and so forth. It's fairly simple. Also want to find the inverse, and we can use that to find the range. Although it's easy to do the transformation and see what happens. We start with the basic function, in this case x. Should know how it looks like. It looks like any logarithmic function with the base which is larger than 1. Now, there are two transformations involved. One is this one, and one is this one. So one is dealing, and one is dealing with negative in front of a natural log. This is basic enough, you can do them in any you like. X minus 2 means shifted to the right, and minus the natural log, that means flipped over. Okay, so with respect to the x-axis. So with that being the case, you can do it in any order. So this is the reflection, and this is moving by how many units? By 2 units to the right. So I hope you see that we can easily recognize the location of the x-intercept, which is 3, 0. There is no y-intercept. Okay. The original log didn't have any y-intercept either. This one with the motion that takes place doesn't have any. And as you look at the vertical asymptote, that is easy to see. Basically, one way to find the vertical asymptote class is to set this one equal to 0. And that gives us the VA equals. Okay, so how do you find the vertical asymptote for any logarithmic function? Set its argument equal to 0. All right. So we have the domain. The range hasn't changed. It's all real numbers. So this is the information that was discussed. It should be obvious from the graph. And I hope everybody is okay with that. So we want to go through the process of finding the in function. It shouldn't take too long. Okay. Before we do, everybody okay with that?
Yeah.
Perfect. So the next step, therefore, is to find the inverse function. So let's start with the next page. Okay, remember f of x is a negative Lx of x minus. It's the same question. We are just continuing with that. As you recall, the first step is replace f of x with y to make life easy. So it's not a big deal. We are changing f of x to y because it makes it easier to do the math. The next step is to interchange x and y. And right here, we do have the inverse, except as you all recall, we just solve for y. And so to do that, first we see a negative sign, we get rid of that, and x becomes minus. Then we are going to rewrite this in an exponential form. Can anybody tell me how we would write an exponential form, class?
I'm sorry, can you repeat that? You broke up a little bit.
All right. We are going to find f inverse. To do that, the first step, we replace f of x with y. The second step is to interchange x and y. So we see a negative sign here. We move it to the other side. Now we are looking at natural log of y minus 2 equals minus x. Is everybody okay with that so far?
Yes, thank you.
Yes.
My pleasure. Can anybody tell me how we rewrite this in an exponential format? Because then practically with that. What's your next step? You are trying to solve for y. Therefore, you have to rewrite the same thing in an exponential form. What happens next?
E with the exponent negative x equals y minus 2.
Perfect. Perfect. Done. You just move the negative 2 and it becomes positive 2 on the other side, and you call y inverse. That's everybody. Now, of course, if you were to graph, you could see side by side using the same set of axes. Okay, we already have the logarithmic function, the exponential function. If you go through the process starting with e to the power of x, okay, then e to the power of minus x flips over with respect to the y-axis, and plus 2 shifts it up by 2 units, which gives rise to the new horizontal asymptote, which is y equals 2. So I hope you can see that. I hope you remember the transformation we did on a couple of questions regarding exponential functions. So we have the information as far as the x-intercept. It didn't have an x-intercept to begin with, the exponential function, because it has moved up. Same thing happens. The domain for the green piece is still the same thing, all real numbers, but the y, which is normally 0 to infinity, as a result of that +2, or as a result of having a new asymptote, horizontal asymptote of y equals 2, has shifted up. So the range is now 2 to infinity. Sounds good, everybody?
Yeah.
Yeah.
All right, we're going to move on. Here's the next one, which is very similar to the previous one. There are some transformations involved. It's not a big deal. We're going to go through that. And we want to find the inverse. Remember, I don't see any base, which means I'm dealing with a common log. Okay. So a common log, basically, the graph looks similar to y equals log x base 2, let's say. So you should know it looks very similar to that. Now, of course, remember what happens. The larger the base, the closer to the x-axis. Why is that? Because the y coordinate for the same x becomes smaller when you have a larger base. So with that being the case, there are a couple of transformations. One of them comes from x minus 1. Okay, that is shifting to the right by 1 unit. The other one comes from number 3, that is going to stretch it by a factor of 3, and so those are simple cases. So we have moving to the right by 1, and it's stretching a vertical stretch by a factor of any number sitting in front of the function. In this case, log function in front of it is number 3. So we can quickly see what happens to the x-intercept, which was 1, 0. Now it has shifted to the right. Therefore, the x-intercept now is 2, 0. I hope everybody can see that. So same thing as before. There was no y-intercept. And the range hasn't changed. But what has changed, because we are shifting it to the right, the vertical asymptote, which was x equals 0, now it's x equals 1. The domain that was 0 to infinity, now it's 1 to infinity. So those are the changes that are, I hope, easy to see. And I hope you realize that simply from the graph or from the transformation. So it's really not big of a deal. I want to move on and find the F inverse. Is everybody okay with this?
Yeah, I got it.
Yeah.
We got a couple of minutes.
Go ahead.
Thank you.
My pleasure. All right. We want to find the inverse function, which means we are going to do the same thing. Okay. And that means f of x is given. We change that to y. Okay. The order is not proper here. All right. So we will look at those graphs in a moment. And let's start with, by the way, just for the sake of argument, so you see, as far as the graph is concerned, you have the graph of 3 log of x minus 1. So its inverse is symmetric with respect to the line y equals x. So you should be able to graph that just using symmetry, number 1. Number 2, as you see, the blue one, the logarithmic function has the x-intercept 2, 0. then its inverse has to have the 0.02. So that right away gives you the idea how you arrive at that. And the same thing, you can look at the domain, make a decision for the range. You can look at the range, make a decision for the domain, and the rest of the stuff. So with that being the case, those two cases, as you can see, are very straightforward. We shouldn't have anything to worry about. However, finding the inverse, we call it y because it makes life easy. We interchange x and y because that's how we find the inverse. So x is equal to log of y minus 1. And before we move on to the next step of finding the exponential format, we need to get rid of number 3, so we divide by it. So x over 3 now is equal to log. In other words, we are isolating the log. In fact, when we want to solve logarithmic equations, when we have log on one side and there is nothing else except some numbers, all you have to do, move everything to the other side and go to the exponential format. How would you write the exponential format for this case class? Anyone? Okay. So log, don't see a base, that means a common log. So 10 to the power of x over 3 is the argument, which is y minus 1. And so we move the negative 1 to the right, and we change the name to f inverse. And we're done. Any questions, class?
So it wouldn't be E, it'd be 10 because it's log, right?
Because the base, okay, when we have log, no base, the base is 10, it's called common log. When we have ln, that means the base is E,
Oh, okay.
natural log.
All right.
Sure. Sounds good, everybody?
Yeah, I got
We're
it.
gonna move on. All right. Let's move on and see what happens. So here's the question. Excuse me. Give me a second. All right. Now we want to solve these logarithmic equations. And the first one, basically, you have to rewrite it in an exponential form. And so how would you rewrite this class? Can you give me the first step, rewriting this?
For part A, would it be
Part A, yeah.
2 to the power of 3 equals 2x plus 1?
Beautiful. And practically you're done. 2 cubed is 8. Plus 1 goes to the other side, becomes minus 1. And that's 7 divided by 2 is 7/2. And you're done. One thing I want to make sure everybody understands, when it comes to logs, you got to be very careful with your answer. Your answer, you have two choices. Check it by putting it in, make sure it works, or just be careful. Anything that you claim to be the answer, make sure doesn't make the argument negative or 0. So if you come up with any answer that the argument becomes 0 or negative, that one is an extraneous solution. So if we were to check it, we would put back in everything and we see that the parentheses is simplified to number 8 and it checks. So that's very straightforward. Can anybody tell us how we do rewrite part B in an exponential form?
X cubed equals 343.
Beautiful. Okay. Again, this is simple enough that we should be able to see it. If not, you have to use a calculator. The right side is 7 cubed. And because they have the same exponent, they must have the same base. And so the answer is x equals 7. Now, if the number is large, it's hard to see. Obviously, you can use a calculator, but again, point being, it's simple enough that we don't need a calculator. All right. Let's give everybody a moment to do this. And I'm going to pause the recording for a minute. So the first step is to do what, class?
You have to
Anyone?
rewrite it.
Not yet. Step 1.
So you get rid of the 2.
Beautiful.
Add it on both sides.
Perfect. Now you are going to rewrite both sides using logarithmic form, or you can say I'm going to take the log of both sides. Because the left side has base e, you take a natural log. So can you tell me what becomes of the next step? Anyone? How would you rewrite this? Okay. Go ahead.
That wouldn't make sense. No, never mind. That wouldn't make sense.
If you take a natural log, or if you rewrite it, natural log of the left side is 3x and the right side is ln 3. So x is simply ln 3 divided by 3. And that's fine with me. The approximation, if you use a calculator, you normally want to go with 4 maybe decimals to be on the safe side.
I
And
was
that
gonna
would be
say,
the answer.
I was gonna say have it 3x equals 1 because 3 to the power technically equal 0.366.
No,
No, okay.
because your base is e. You can't change the base. The base on the left side is e.
No, I wasn't talking about the base. Oh, I see. They have to be.
I mean, you know, you gotta stick with the given base. If the base is not given, you may be able to make up something. But first you look at the left side. By left side, I am referring to this one. The left side of this equation already has base e, which you can't change, okay? Now, again, if you remember logarithmic properties, you can take a natural log of both sides. The left side gives you 3x and the right side is simply ln 3. All right, we need to move on. Can somebody read this question for us, please?
According to scientific research, the percent of the course that one remembers after the conclusion of the course is approximated by the equation RT equals 85 minus 41.9 log t plus 1, for 0 is less than or equal to t, which is less than or equal to 48. Find the percentage of the course that one will remember after A, 10 months, B, 25 months.
Thank you so much. I hope you see why I picked up this question again, to emphasize the importance of studying and sticking with it, because that's the nature of human being. So what happens after 10 months? All you have to do, replace the t with 10. Agreed, class?
Yes.
So there's nothing we can do. We just use a calculator. So 85 minus 41.9 times log of 11. Using a calculator, we end up with 41.3656, and that means percent. So this one obviously is log 11, okay, class? So after 10 months, on the average, the percent of the course that one remembers is about 41%. Now imagine what happens after 25. You go through the process. Of course, this is log 26. You use a calculator, about 25, 26%. And that should be alarming. I hope everybody see why I picked up this question, because you're a student, you should recognize this. And the only way you can change, and by the way, this is based on a study. It doesn't mean that it happens to everybody. It's just that most students, this is what happens to them. But can you change that? Absolutely. And it's up to you. Okay, it is up to you that you do study properly and you stick with it. I mean, just for the sake of argument, quickly, we're going to look at logarithmic properties in the next section. How many of those properties do you remember from intermediate algebra? It depends how you did this study. All right, I'm assuming we are okay and done with this.
Yeah.
Yes.
Thank you, everyone. Can somebody read this question for us? This definition, please. Go ahead.
The pH represents the measure of acidity and alkalinity of a solution. A number between 0 and 7 indicates acidity. Lower numbers indicate stronger acidity. A number between 7 and 14 indicates alkalinity. Higher numbers indicate stronger alkalinity. According to this scale, a value of 7 represents neutrality, like water. It is roughly the negative of the logarithm of base 10 and the molar concentration, whether in units, measured in units of moles per liter of hydrogen ions. Hydronium ion concentration, H3O plus. pH equals minus log H3O plus. Find the pH of a solution whose hydronium ion concentration is 2.8 times 10 minus 3, exponent minus 3.
Thank you so much. This is the definition of pH. Again, you may remember it from intermediate algebra. Basically, acidity and whether a liquid is acid or base. If it's between 0 and 7, it's considered acid. If it's between 7 and 14, it is considered a base. Okay. So all you have to do, plug in minus log and plug in the number. And at this point, you really can use a calculator, class. You can use a calculator to come up with the answer. But I want you to understand, we are moving towards the next section on the properties. I want to quickly remind you of a property of log, which is called the product rule. In case you don't have a calculator, and at the very least, you want to recognize whether you're dealing with acid or base. And so here's what happens. 2.8 times 10 to the power of negative 8. You can say log of 2.8 and log of 10 to the power of negative 3. You keep the negative sign out. And so what is the log of 10 to any exponent? That is the exponent. And so this is your answer. So you may not know the precise, and well, you may have to use a calculator to come up with the answer to what is the pH, but you should recognize that this number is less than 7. And how do you recognize it? Because minus log 2.8 will take away from 3 and makes it 2 point something, okay? And by the way, log 1 is 0, log 10 is 1. So log 2.8 is between 0 and 1. So minus a number between 0 and 1 takes number 3 and makes it to 2 point something, which is less than 7, and it becomes acid. Now, do you have to do it this way? Well, not really. I'm showing you in case you want to use the properties to see what happens. So you can go from here using a calculator. Using a calculator, okay? Please mute your audio, everybody. Mute your audio and just turn it on when you want to ask a question. So we don't have a feedback. Mute all the audio. So this is the answer. Is everybody okay with that?
Yes.
All right, class. So we are looking at 5.5, properties of logs. We discussed those sections that you see here. And we're going to move on to 5.5. So what you're looking at is a lot of properties here, all of which have been discussed in both courses, intermediate algebra as well as college algebra. And first and foremost, the definition of a log, okay? Then I want you to look at the left side, okay, and see the general form. So we're going to quickly go over that. Log 1 with any base is 0. And why is that? By definition, in the form of a exponential, b to the power of 0 is 1. The next one, log b base b is 1. What does it mean? It means if you have the same base, okay, as the argument, the answer is 1. The next two refer to the fact that logarithmic functions and exponential functions are inverse functions. Okay. We've seen the proof in intermediate algebra, and you're more than welcome to ask me to go over the proof if you want during the office hours. The next one is called the product rule. Log xy base b is log x plus log y. Both of them have the same base b. And log x over y is log x minus log y, having the same base. All of them have the same base, namely b. And finally, log of x to the power of n with base b is n log x base b, meaning the exponent becomes a coefficient. Now, this is a general form, class. This is a general form. Now, two specific ones. One of them is a common log. Why is it specific? Because the base is 10. And one of them is a natural log because the base is e. And I hope you can find this nice and easy as far as the transition is concerned. So you should be able to come up with a common log, natural log, and all those properties. So to quickly recap that, the first one is the same, log 1 is 0 or ln 1 is 0. It is the second one that sometimes students have a problem with. When we say log b base b is 1, then for common log, it's log 10, which is 1. Why is that? Because we know the base is 10. For natural log, it's ln e, which is 1. All right. Then the next three for the common log, those are just the same as before. You don't write the base. That's all. Now for the two that refer to the fact that the two functions are inverse of each other. So this is log 10 to the power of x equals x, and the next one is 10 to the power of log x equals x. And that's something you want to be careful when it comes to natural log. As long as you can do that, it's fine. Now, the rest of it is very simple. Instead of log, just write ln. Finally, at the bottom of the page to the right, we see a change of base formula. Change of base. So if log x has base b, you can write log x at top, log b at the bottom, and choose any base. For example, something made up like a. But normally, we want it for the evaluation, we use either common log, so we don't write the base and the base is 10, like log x over log b, or we use the natural log ln x over ln b. Refreshing your memory about the graphs of logs versus exponentials. So if you're looking at, for example, natural log, clearly it's negative when x is between 0 and 1. It's equal to 1 when ln x is 0, and when ln x is positive, x is larger than 1. So the graph tells us everything we need to know. Also, what you see at the top is what we go over in calculus. I'm going to mention it here. The curve y equals e to the power of x, if we were to draw what's called a tangent line, at that point, that we will be discussing in the next course, that happened to have a slope of 1. We will look at that. And if you look at y equals ln x, that happened to have the same slope, but instead of that, remember that 0, 1 translates to 1, 0. I want to go over the next page. It happens fairly fast. I was hoping that we do more. It didn't happen. So we have a lot to do next time. So we have to show up to do that. So let's actually do at least one page. So knowing the properties, and by next time, if you haven't already, you should be very comfortable with this. Okay, class? We want to rewrite this. Can anybody tell us what's the answer for part A?
It's 3.
Beautiful. Beautiful. Part B?
Square root 3.
Perfect. And part C?
0.35t.
Excellent. Thank you so much. All right. So let's give everybody a moment to answer those questions. You can even do it in your head. I want to make sure you have an idea what the answer is supposed to be, and we can move on. So answering A, B, C should help us with the rest of them. Okay. So again, we used some properties. We're going to use other types of properties. By the way, part E uses the same property, okay? Or for that matter, part F. But part D is slightly different, okay? So for part D, the exponent becomes the coefficient. Okay, 3 sits in front. In this case, the exponent sits in front too. The rest of them, E and F, you just have the answer in the following manner. This is 7 and X because we have the same base. So a number to the power of log, when log has the same base, it can undo the process and gives you the argument. The same thing works out with part F. All right, class, that sounds good. Is there any questions?
No.
All right, let's stop at this point.